with minimal interaction, so it's not distracting. I can also set up reminders. I did not bring my row sheet, okay, but if I did, I can do something like, okay, Google, remind me to take row at 9:30. Okay, it took that, but it said, remind me to take pill at 9:30. Okay, but close enough, right? I mean, at 9:30, it would buzz me on my wrist and display the text, so I would know, oh, okay, I need to take row, okay? So I think it is, there's value to it. Whether it's worth the money, that's a whole different story. I have 2 weeks to evaluate it, okay? Because with Best Buy, you get 2 weeks, and if you don't want it, you can return it. So we'll see. But there are alternatives too, and there are less expensive options of this and whatnot. All right. So this is kind of that's from the other class. We were talking about. It is kind of not related to this class, but in a way it is. We were talking about abstraction in terms of programming, and this has to do with the conversion between polar coordinate versus the XY coordinate, which is something that we are used to. So it's for a class. It's kind of interesting. All right, this stuff we have talked about. So before we go anywhere else, I'm going to give you the new homework assignment, because I think this is going to be a useful homework assignment, not only to prepare you for the exam, but also it will have a lot of how should I put it? It will have a lot of impact, to the rest of the semester. So this is going to be a really helpful homework assignment. Okay, so the new homework assignment is not visible to you just yet because I'm still editing it. But as I continue to edit it, I can show you what it is. It's almost done. I just have not shown it to everybody yet. So let me just maximize the screen. There's one button to maximize. There we go. Okay, and I can make it even bigger by taking away the frame of the browser itself. So this is your new homework assignment. I can bump up the font size, I think. Yep, there you go. Okay, one mode of addressing relies on the content of one location to locate the actual location where the content needs to be stored in another register, possibly another register. In C and C++, we know this as dereferencing a pointer. In this assignment, we'll do this with the toy computer architecture, the processor architecture. There's an updated file, so definitely right-click on that link, download the updated toy architecture, and use the new architecture. Specifically, in this assignment, I'm reading the second paragraph, store the content of RAM location 0 into register B, which is the second register in the register bank. Then use the value of reg B as the address of the content to store in reg D. So use reg B as a pointer, okay? So that reg D, in the end, will get the content at the location pointed to by reg B. The C code does not show very well here because it's not getting through the filter that needs to go through. So, but you can still read it. I mean, this is still pretty much the same code that it would display otherwise, but just without syntax highlighting. So the first instruction, or the first sequence, is going to say, reg B gets whatever is stored at location 0. Now, I don't have any typecasting here intentionally, because in assembly language programming, there is no such thing as type. Okay, so that's one thing that we will have to remind ourselves from time to time as we move forward to talk about assembly language programming. But reg B is just going to store whatever location 0 has, okay? And then after that, I want to use reg B as a pointer, dereference that, and store whatever reg B is pointing to into reg D, okay? When I show you the architecture, it will be clear what I mean by that. The rest of the assignment is pretty much the same stuff as we talked about last time. In this assignment, start by doing the above operation by hand, then download and save the microcode planning template spreadsheet. Some people forgot to rename the file, okay, for the fetch cycle. I did not take any points off, okay? I just kind of noted that and go like, well, it should be a different file name. In the spreadsheet, blah, 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 so that part is still the same, except in this case, I also want you to keep power consumption in consideration. In other words, turn off the enables unless it needs to be turned on. Okay, so that's for power consumption consideration. Not so much whether it's correct or not, but I want it to be power saving as well. Because I don't want any one of you with no concept of power consumption to design the next Snapdragon on the watch like this. I want you guys to design the best, the most power efficient processor, so that I can have that in my pacemaker when it's time to install a pacemaker. Yep, and of course there will be a control panel on my watch of my pacemaker. It's like, yes, I want a boost, and it goes like that. I want a 15 PSI boost. Screw up the turbo, man. That'll be pretty funny. The spreadsheet should be done so that the first row assumes the processor is just reset by an external source. Okay, so same as last time. Oh, forgot to change the fetch over here, so we have to change it to indirect. And let me just pick the font. That's the font control right there. All right, so are there any questions about the description of this homework before I go ahead and show you the quote-unquote new architecture? There were some minor changes from last time. I just want to point out the minor changes. Yep.
So it's basically the same, except that in the last assignment, we were not to change anything in the registers.
Correct, yes. But this time you still don't want to change things that you're not supposed to. For instance, the address register should not be used here. Okay, so there are certain things that you should not be changing, and don't change those. And let's see. Oh, the microcode planning template also has changed because we added one more multiplexer into the design. So the control signal of that one multiplexer is also in the new spreadsheet. So you have to specify that as well. Okay. All right, so any other questions on the description of the homework assignment? No questions? All right. So if there are no questions about this, we'll go ahead and actually look at the new design. Oh, no, wrong link here. I need to unmaximize, which is here. Save it. Oh, and one more thing. I need to make it invisible. And save it. Save and display. This is how I can click on the links. So I'll go ahead and click on the architecture first. Save link as. Put it into the 10 folder. Okay, that sounds good. And now I can start up Java to work on it. And I can actually supply the file name, on the same line. So this way it will open up LogicSim and also the file at the same time. There we go. So this is, there we go. Oh, wrong. There we go. So this is the new mux that I added to the design. Let me just highlight which one we're talking about here. So this is a new mux because I want the input to the register bank to come from both the ALU, which is the result of the calculation, but I also wanted to come directly from the data bus. So that's why we have two paths going into the mux, and the mux will merge, well, I should say select one of the two paths to actually connect to the input of the input register. It is important for this homework assignment, so you have to remember to specify, what is reg in mux cell, okay? It's register input multiplexer select. That's why it's named that way. The other change that I also made to this design has to do with, we talked about this already, but I actually made a change. It has to do with the PC, or the program counter. So the program counter in this case is, well, actually this does not impact what we're doing because I don't need you to do the fetch cycle anymore in this homework assignment. But just to note, there's a change. Instead of having the trigger on rising edge, it is now on a falling edge. Okay, and the reason why I did this is so that we don't end up with a potential raise condition that we talked about last time. Okay, so there's a raise condition that can happen, from the previous design. There's not much you can do in software except to break it up into 2 clock cycles, which is going to be very, very inefficient. This is much more efficient. because we are still only using one clock cycle for fetch, but at the same time, we don't have a potential of a race condition anymore. So I'm optimizing the design a little bit to make it work a little better. And then there's one more change, but that one we also have talked about already. It's nothing surprising. It's inside the registers. So if I show you the registers, this is what we have talked about also, because last time when we did any changes, it updated all of the registers. And that's because when the disabled output is not 0, instead it's floating, it floats high for some reason. Okay, so all of the registers were actually listening to the input of the register, and they all got updated. Okay, so that's also one change. This one does quote unquote impact your homework assignment in the way that it fixes the design. Okay, so it is actually this is the correct way of doing it. So when you work on this homework assignment, make sure you use the new version of the processor architecture and not the last one. Okay, the new one has a different file name, so it's pretty hard to mistake this one for the old one, because when you look at the file name, this one has the date of the design on it, which is today. Okay, so make sure that you use the new design and not the old one as the basis of this homework assignment. Are there any questions at this point? Okay, let's take a look at the RAM here, because I have to go back to main first. So when you look at the RAM content, okay, this is not helping. So when you work on this homework assignment, one thing you have to do, because I cannot save it, okay, the content of RAM cannot be saved, not into the same file, okay, I have to save it into a different file. So what you need to do is to change location 0. The way it is right now will work, except it doesn't really show you that it is working. So what you need to do is to change location 0 to point to another location. So I'll just pick a random location here. So let's say it points to location, just pick one, 07, okay? So that's the content of location 0. So what you need to do is to now go to location 7, which is this one here, and put another value into it. Let's say FE, okay? So what your sequence of clocks has to do is to put 07 into reg B first inside the register bank, okay? And then after that, you will have to use that 07 to go to location 07, which permanently has the content of FE, and FE itself has to be stored in reg D. That is the purpose of this homework assignment. Are there any questions about what your microcode or what your sequences is supposed to do? Okay, so dereference location 0 first. Put the content of location 0 into reg B, and then use reg B as an address. Go to the location and then store the content of that location into reg D. So if I were to do this, just manually doctor everything, that means inside the register bank, this is what's going to happen. So inside the register bank, this is what's going to happen. You will first basically put 07 into here, okay? So obviously you cannot turn in the homework by doing this, because this is not expressed in the control signals, right? So this will be the first step, okay? You have to make sure that this happens first. And then after that, reg D, which is this one here, is going to end up with the value at location 7, which is FE. So that's the effect of what your homework assignment needs to accomplish. Are there any questions about this? So to get started with this homework assignment, just in case someone needs to, have a little clue of how to get started with this, the best way to get started with this is to look at this overall picture and draw a line, okay? Because you need to go into the registers, and this is the only path going into the register. So what you need to do is to say, okay, since this port here is reg in, which is the data input port of all the registers, you click on it, okay? And it ends up here. But you know the content that needs to go into reg B and also eventually reg D comes from the memory, which is on this path here. So now the question is, how do I complete that path? What else is on that path that I have to turn off so that I don't end up with a bus fight or accidentally updating a register that I'm not supposed to? So you can think along that line and go like, okay, I'll turn off everything first, and then I'll only enable the stuff that is needed to get this done. Okay, so that's one way to do it, and it's kind of graphical. If you print this out, you can actually highlight it with a highlighter, and that will help you decide what needs to be changed in order to do this. Are there any questions at this point? Yep.
So we don't have to change like the program counter and...
No, you do not have to change the program counter or load anything into the instruction register. This only has to do with Reg B and Reg D inside the register bank. So don't change anything other than those two registers, and don't end up with a bus fight condition. Okay. Yep.
So since like the registers will like update on a rising edge after when you get to 1 for the clock, is that when it's safe to turn off things that are now like done?
Correct. Yes. So you want to turn off things that are already done, because then you're not affecting anything other than what this is supposed to do. Another clue is you cannot do this in 1 clock cycle, so don't even try. Okay, it has to be done in multiple clock cycles. What is the clue that tells you this cannot be done in a single clock cycle? There's no way you can do it in 1 single clock cycle. What is the resource that is restricting that from happening? There are actually multiple resources that are restricting this. The multiplexer is one. Well, the register bank is one too, because the register bank only has one data input port, right? But we have to update 2 registers. Well, how do you update a register? Rising edge. But there's only one rising edge for each clock cycle. So in order to update 2 registers inside the register bank, and because we only have a rising edge to do that, that tells you right away that we have a minimum of 2 clock cycles in order to accomplish what we need to do. Okay? And besides, everything comes from RAM too, right? And how many data buses do we have on the RAM component? Only 1. So that also tells you that we can only that's a contention of resource, and we have to break it up into 2 clock cycles to do this. All right. Any other questions about this? Okay. If there are no questions, this is a good study material for the exam, because it's going to have some of the elements of questions in the exam. So this also makes you kind of understand the design a little bit better too. All right, so I'm going to keep this up, okay, because in case of any questions, we can easily come back and refer to it. And at this point, for the lecture part of this class, we are moving forward to talk about assembly language programming. So finally, we are on to assembly language programming, which is a huge topic. If you click on this one, it is a really long topic. I really should spend some time to break it up, okay? But this is where we actually write code to do something, okay? What is the importance of assembly language programming? Okay, we first talked about this 8 weeks ago, or just about 8 weeks ago in the first class. So I'm pretty sure most of you have forgotten, okay? And I don't blame you, because we haven't really talked about assembly language programming. We focus a lot on transistors, gates, adders, subtractors, multipliers, dividers, and stuff like that. Those are all pretty low-level stuff. So now we are finally getting to assembly language programming. What is connecting what we have learned up to this point to assembly language programming, and what is this connecting to all the other classes that are important to you? So I'm asking you about the why. Okay, why do we have this topic in this class? What do you think? Okay, so you're remembering something from 8 weeks ago. Okay, I showed you, one or two programs that had very strange crashes, right? Okay, it behaves very strangely. The program does not call a particular subroutine, and yet it returns to a subroutine that was not called anywhere within main or within the code itself. Okay. I also showed you one example where when you return to main, all the variables were shifted. Do you guys remember that? Okay. So those are all, unfortunately, realistic symptoms that you may encounter as you write your C, C++ code. Not so much in Java. So if you say, I will never ever program in C or C++, I'm a Java programmer, I only program in Python or something like that, then you can legitimately tell yourself this stuff may not be very applicable. But can you guys say that? Can you say that I will only program in Python because Python is the way to go, nobody should program in C or C++? You may think that, there may be good reasons to think that. To a certain degree, I agree as well. Can you tell your employer that? And say, I don't think C and C++ is a good programming language. I suggest that we rewrite the entire blah, 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 blah in Python. What do you think would be the response of your boss? Well, a good boss would not fire you because of that. Okay, a good boss will ask you for the rationale and appreciate that you have the input and tell you this is all good. It's good that you understand all of these issues. Pointers are not really good things to have. Heap management can be nasty, and all of the other programming languages do not have these issues. But your boss is an employee of the company, unless your boss turns out to be the owner of the company, right? So your boss cannot just say, well, this is a better programming language, let's switch. What is stopping your boss from doing it? Even though your boss values your opinion, understand that you have a valid point, why can't we just say, let's switch to Java? With the cost, exactly, okay? Because the product may have a million lines of code already in it, okay? And converting a product, a million line, software source code from one programming language to another programming language is a major undertaking. Okay, that's a major undertaking. And in the process, you can introduce new problems. Okay, there can be efficiency issues because C and C++, if not for anything else, what it is well known for? Efficiency. Okay, it is really fast because everything is compiled not only to object code, but to the native object code of your processor. Java is compiled too, but it's compiled to what? What is the name of the code coming out of the Java compiler? Bytecode. It's called bytecode, but bytecode cannot be executed by your processor, your i5 processor, your i7 processor, or even your ARM processor does not understand bytecode at all because it is intended for the Java virtual machine, exactly. Okay, and that's why you have the flexibility because now, LogicSim is a very good example. You can run it in Linux, you can run it in OS X, you can run it in Windows, you can run it in just about any modern programming operating system. But you pay the price in terms of performance because it has to go through the Java virtual machine on every single platform in order to get the program running. Okay, but you say, but I don't see any, really, lag or slow down because of that, but that's only because it's an interactive program and you can only specify gates and draw stuff on the design so fast. Okay, but when you're working on number crunching applications, it's a whole different story. Okay, running everything in Java can slow down a system significantly. My watch just buzzed me. Take pill. Okay, yeah. I don't understand. I distinctly said take roll and it said take pill. That's like completely different. Maybe most people take pill and it has a preference to that. I think that's what's happening. I just have to make the roll in the shape of a pill, then it's all okay. Alrighty, so we'll go ahead and get started with this section here. So I'm glad that you guys were making the connection to back to what we talked about earlier, and that's something that we have talked about here. How does this connect to? I opened in a new tab. So where is the new tab? No, that's not it. Okay, to look at my taskbar because it opened it somewhere else. There we go. Okay, so but how? So now we are relating this to C, C++, which is going to be applicable if you have not taken CISP 400 or 430 at this point. This may help you debug your program in those classes. Okay. What about the other stuff that we have talked about up to this point? Everything that we talked about, like transistors, NAND 2 gates, to regular gates and logic gates, and or not, to adders, subtractors, multipliers, dividers, and then eventually we get to multiplexers, we get to RAM modules, registers, and stuff like that. And now we have a very rudimentary architecture of a processor. How does this connect to those concepts? Okay, let me just go back to the design here because I want to show you what we have at this point. And we can just kind of focus more on the design area. We don't need to look at the details, we just need to look at the overall architecture here because it's just a point that I'm trying to make. How does assembly language program relate to this picture?
Instructions for that?
Those are the instructions for this. Exactly, very good, okay? But we're still missing one piece. What is the one piece that we have been working on from the previous homework assignment, the one that's due on Tuesday, and the one that is assigned today? What are we trying to do with those homework assignments? We're trying to come up with the microcode, okay? It's called the microcode. It's not quite the instruction, it's the microcode. So the microcode turns out to be the lowest level instruction, quote unquote instruction, that we can specify because it controls, okay? The microcode controls all of these control signals. Register input select, register output select, ALU select, ALU output enable, and everything like this. Is coordinating all of these components and so that they can accomplish certain tasks, okay? The fetch cycle is accomplishing a particular task. What you're doing with this homework assignment is accomplishing a certain task. So we are trying to figure out all the low-level signals in order to control these components in a particular sequence to accomplish all of those particular tasks. Those steps eventually will become a part of the music box. Do you still remember the music box homework assignment? Except in this case, it's not going to be turning on and off LED segments to display 0 to 9. Instead, what it will be doing is to control all of these signals. So every time the music box click, okay, by one position, it will be turning on and off these signals so that it will accomplish, it will enable pathways from memory into the register bank, for instance. Okay, for reading, it will connect the ALU to the register bank to store the result of a calculation, and so on and so forth. But that part is still missing. Who is going to use the microcode engine? The actual machine code. Okay, so we have two levels of instruction at this level. There's the microcode, which is something that you cannot change as a programmer. Okay, that is built into the processor. It is specifying the lowest level of signals and say, okay, you're going to turn on this first, turn on that, and then turn off these things, clock. And then turn off these things, turn on that thing, clock, and so on. Those are the microcode. But the actual instruction that you specify as a software developer is at the instruction level, okay? Not microcode, but instruction level. So the instruction is going to be decoded by a decoder so that the processor will look at the instruction and it will say, oh, based on the zeros and ones of this instruction, we'll map it to those particular microcode, and it will clock through those microcode individually to quote unquote execute a single instruction. Are there any questions about this? If you want to think about it in a certain way, okay, you can say that we have a table, we have drums of music box, drums, okay? So each instruction has its own little drum. Your instructions, which is a binary code, is kind of a way to index into a box that has, let's say, 16 or 32 of these little drums. So by specifying the binary code of a particular instruction, the processor is going to look at your instruction, which you can specify as a software developer and say, oh, I see that you want to retrieve drum number 5. Okay, pick up drum number 5, put it into the music box mechanism, start playing it. Okay, after that is played, the processor will put the number 5 back into the box and look at the next instruction and say, oh, the next instruction is trying to use drum number 12. Okay, pick up drum number 12, put it into the music box, let it play, and then put it back in the box. Okay, so your actual software instruction is an index into the box of drums. Okay, and then each step in the drum is a microcode that the processor has to go through in order to accomplish what it needs to do. Are we still doing okay with this analogy? Is it helping or is it hurting? Because sometimes I come up with ideas of how to explain something and it turns out to be worse than not having that analogy. Is this okay so far? Okay, all right. All right, so the next thing we'll do is to give you an idea of what the binary code would look like and then we'll go ahead and talk about assembly language programming in general. And we'll do this here. So instead of using the Intel architecture, which has a really kind of messy instruction set, I'm going to use one that has a relatively clean instruction set, just as an example. Okay, it's called the AVR Architecture. AVR instructions of code. I should retrieve something. There we go. And by the way, this is one of my favorite architectures. Just from the get-go, instruction set nomenclature. I think some of you recognize some of these terms already. In fact, if you look at this, you go like, oh, we have seen that. Oh, we have seen that too. Okay, let's just kind of go through some of these because I do want to give you constant reminders of stuff that we have talked about. Carry flag. Have we talked about the carry flag?
Yes.
Yeah. The zero flag, I think we talked about it, just not a whole lot. Negative flag, which is known as the sign flag for us. Okay, we talked about the sign flag, which is the most significant bit of the result of an addition or subtraction. Two's complement overflow indicator. This is our O flag. Okay, so Intel wants to call this the O flag for overflow, and then the AVR architecture calls this the V flag because O looks like a zero, and that's why they're trying to avoid the use of uppercase O. But it's the same thing. This one is cute because it looks completely foreign to us if we stick with the nomenclature of Intel. But when you look at the meaning, I cannot select it, right? I need my gaming mouse. I need to convince the department that I need the precision of a gaming mouse because I can't select stuff on the screen correctly. So this one we have seen already. It's just that the nomenclature or the character that we chose is completely different. S turns out to be the L flag that we have talked about. N is the sign flag, which is the S flag in Intel's nomenclature. And then V is O, which is the overflow. This is how we can test signed numbers to see if the second number is greater than the first number. Okay, so all of these things are in a status register. The Intel architecture has a different nomenclature for the status register, but it's the same thing. It's called the flag register in the Intel nomenclature. But something is storing the results, okay? Certain aspects of the result of a comparison or subtraction or an addition. We have registers. Now, in this case, we have RD and RR, okay? Destination and source register. That's because the AVR architecture is a RISC architecture. It has 32 general purpose registers. So that makes it easy because you just refer to the registers as register 0, register 1, all the way to register 31. The Intel architecture has A, B, C, D, but that's not really A, B, C, D. A is accumulator, B is base, C is counter, and then D is destination, I think. So the so-called ABCD registers of the Intel architecture are not general purpose registers. They are actually special purpose registers, and then later on turn into general purpose. So we'll deal with that later too. But what I want to do is to show you the actual opcode. Okay, so let's see if this will do it. It's not showing the actual opcode. I'm looking for the actual opcode here. There we go. Okay, so this is these are the actual opcode. We'll pick one that we are familiar with or should be familiar with in shift. And okay, add is good. Okay, we'll just pick this one. All right. So this is the add instruction. So we'll just focus on this instruction here. When you look at the description, it's not really that complicated. It adds 2 registers without the C flag, so the C flag is basically assumed to be 0, and places the result in the destination register RD. So what it does is to pick up, you have to specify 2 registers. One is RD, the destination register. One is the source register, which is RR. You will do the addition and then store the result back into RD. In C++ terminology, it is the same thing as RD plus equal to RR, okay, because we're assigning the result back to one of the registers. I don't want you to read the syntax just yet, okay? So this part, we'll just kind of ignore that for now. I want you to look at the 16-bit opcode, okay? The 16-bit opcode looks like this, okay? 0, 0, 0, 0, constant 4 zeros, 1, 1, which is constant, and then we have RD, and then we have D, 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 and then R, 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 R. Those are the bit patterns that you, as a software developer, has to specify so that the processor understands, oh, I need to retrieve the drum that will basically connect RD and RR from the register bank to the two inputs of the ALU, connect the output of the ALU back into the input of the register bank, okay, and clock. Okay, so the processor, which is the processor architecture that is currently lacking, is we don't have the decode logic to look at 0, 0, 0, 0, 1, 1 as the first part of the opcode and say, oh, I want to retrieve drum number 3 of the box of drums. Okay, we don't have that ability yet. But assuming that we do, which register, which is already present in the architecture that we have at this point, which register do you think is going to store this opcode? And by the way, an opcode is also called an instruction. That should be a big clue. The instruction register, very good. So the instruction register is a holding place to store the instruction to be executed, or the opcode to be executed. Do we connect the output of the instruction register to anything in the current architecture? The answer is no, okay? So when we are done with the architecture, it will be connected to a decoder, and then the decoder will have an indexing mechanism to retrieve the right drum of microcode to execute when we encounter an instruction like that. Is that okay so far? All right. So let's take a look at another instruction that is related to your current homework assignment. Okay. So we'll take a look at. Let me see. It's not going to be exactly the same, but it will be close to what we're going to do. It's called the LD instruction. So I'm just looking for LD. It's probably indexed somewhere, but too lazy to look it up. LD, okay, load indirect from data space to register using index Y. So it's not exactly the same, but it's close to what we are about to do. So there are several variants of this. I'm going to pick the one that is the easiest, which is the first variant. Okay. In this case, Y is a 16-bit register instead of an 8-bit register, but other than that, it is the same thing as what we do with our architecture. Okay. So when you look at the operation, let's focus on the operation first. So the operation is to dereference register Y. So go to whatever location Y is pointing to, retrieve the content of that location, and store that into register D. And then when you look at the opcode, the 16-bit opcode, it looks like this. So this means, you know, this bit pattern has to be loaded into, actually I have to specify both locations. Let me just do that. So what is happening is all this will have to be loaded into the instruction register, and for this particular architecture, the instruction register, I need my gaming mouse. Come on. Come on. There we go. All right. So these 16 bits together is the opcode, okay? Unlike our architecture, which currently only has 8-bit as the instruction register, this will require a 16-bit instruction register. Upon decoding this particular bit pattern, the processor will now understand, oh, we want to load indirect from register Y into register 0 to 31. It will retrieve that particular drum, put it into the microcode engine, let it roll, okay? It'll execute all the microcode steps to accomplish what this instruction has to do. Is that okay? All right. So the next question now is, if you have to write your programs using these ones and zeros, the bit patterns for the individual instructions, would you prefer that? Okay, now remember, you're not only going to specify registers using a bit pattern, you're also specifying the rest of the instructions using bits, using zeros and ones. So in this case, if you want to load indirect from a 16-bit register into a particular destination register, you have to remember, as a programmer, you have to remember it starts with 1000, 000, and then you use these 5 bits to specify the destination register, because 5 bits can specify 1 out of 32 registers. And then after that, you have 1000 as the end. So you have to remember that pattern. So let me ask you, what was the bit pattern for add? I like that answer. I remember actually, it's 00011 RD RRRR DDDD. But you can ask me about the jump instruction. I have no idea what the jump instruction is. It's in terms of opcode. How many opcode can you remember until your brain starts to fry? It's like, I cannot remember anymore. It doesn't take long, right? So, but are you guys making the connection from the architecture that we are currently working on to the lowest level of specification of instructions, which are basically just bit patterns? Okay? Now, when we're getting to jumps and stuff like that, it gets worse. Because when you're dealing with jumps, okay, let me go retrieve a jump instruction here. And by the way, jumps are equivalent to go-tos in C and C++. That's a jump instruction. Jump to an address, which means continue execution at a certain address. And the bit pattern looks like this. This is a 32-bit opcode because it requires K, 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 K. So all the Ks will basically specify the new location to continue execution. In other words, K, if you combine all the bits labeled K, collectively they specify an address to continue execution. But who is going to specify that address? You are the developer, so you know where it's supposed to go, which also means you have to keep track of the location or the address of every single opcode that you have specified in this program. But what if you're trying to specify a conditional statement where this is the conditional part, and you have to say, oh, if the condition is false, I want to go to the else case. Where's the label? Where is the instruction? Or what is the address of the else branch? I don't know yet because I haven't even specified the then branch yet. So what do you have to do as a programmer? You make a note and say, come back to do, okay, fix this. Because you don't know, you have not written out the program yet to know the destination of where you want to branch. Is that making any sense? So you continue to write the program, you write the then branch, right? After the then branch, then you start to work on the else branch. At that point, you know the address of the else branch, then you come back here and remove the to-do label and say, okay, it is location da 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 da, which is going to be a number, right? So you write the entire program like this. And then later on, you found out that, oh, I just made a mistake with the then branch. I need more instructions in the then branch. What is going to happen? How is this instruction going to be impacted when you go back and change it?
What else needs to change?
Everything after that needs to change. And guess who's doing it? You, the programmer, the developer is going to do is to have to track all of these things. Okay, so you can kind of imagine writing a program this way is not going to be very effective. Okay, because as a programmer, there are so many things you have to track. What if you make a mistake? What if you count the instructions wrong, off by 1? Is anyone going to tell you, hey, Tack, I think you miscounted by 1? No, there'll be no warnings. So how would you know that your program has a problem like that you miscounted 1 location? It's not going to work right? The program is going to work incorrectly because you branch too early or too late. Okay, go to a location that's too early, too far back, too much to the forward, and stuff like that. So it's not a very good way to do it. You can do it. It's just not a very preferred method of writing programs. Okay. So the next question is: are we going to write code program like this for the rest of this semester? Well, what do you guys want to do? Do you want to do it this way? So you have to count every single location, and every time you fix the program, you have to say, I have to update 20 jump instructions because they're all affected by making this code longer. So you don't have to do that. Why not? because we can now use the mnemonics. This is called the mnemonics. So instead of having to remember the bit pattern, which is 1001, 010, a whole bunch of bits, and then a 110, and then a whole bunch of bits, you just have to say, oh, this is JMP. This is the jump instruction. So JMP as a word is called the mnemonic of this instruction. Is that okay so far? Yep.
Is it like a pattern defined and constant? So
It's sort of like that, but it does a lot more than that. Okay, it's called the mnemonic of this instruction, and there are multiple instructions of the same mnemonic. So for add, there are multiple add instructions of the same mnemonic because they all do about the same thing. Okay, and the way you spell mnemonic, let me just go retrieve that because I want to show you what is the word mnemonic? It's N-M-E and then mnemonic. Well, Google can fix that. Nope, I got it right the first time. Woohoo! Okay, a device such as a pattern of letters, ideas, or associations assist in remembering something, and that's exactly what it is. Okay, because to us, JMP, even though it's missing a U, it's still a whole lot easier to remember than 1001, 011, a whole bunch of W's, and then 001, and then another bunch of W's. Okay, it's a whole lot easier to remember because jump is JMP. Is that okay so far? Okay. Well, if you have an assembler, which is the tool, it's like a compiler, okay? In many, many ways, an assembler is a compiler. It goes through the mnemonic stuff that you type. So you, instead of writing the program like all the zeros and ones, now you're writing the program using mnemonics, okay? So you have add, you have jump, you have load, LDD, which is load indirect, and so on. Somebody has to translate that into the actual machine code. The assembler is the tool to do that. So the assembler is just like a compiler. It translates the source code written in mnemonics into the object code, which is actually the bit pattern, the zeros and ones for the individual instructions. Is that part okay? But on top of that, in addition to translating from JMP to the zeros and ones that we need, the assembler can also keep track of locations. So instead of having you to remember, oh, the branch destination or the jump destination is over here, and you have to count individual instructions or bytes, now you can just say, oh, let's put a label here, okay, which is a symbolic name. So you put a label at the destination. Now you can insert and delete instructions all you want between the jump and the label where it needs to go, and then the assembler is the one who's going to count. That makes things so much easier, right? Because you don't have to count anymore. You can focus on, well, you can focus more on the logic of the flow of the program and less on the details of counting individual instructions. Is that okay so far? Yeah, just the concept? Okay. All right. So with all that said, the next question is, do people actually program in zeros and ones? Well, what do you think? What about the first computers? This is a chicken and egg problem, isn't it? Because what do you need to run an assembler, which is the fantastic tool that can understand mnemonics and keep track of labels and stuff like that? So what do you need to run the assembler? A computer, right? A computer, right? So what about the assembler itself as a program? Who wrote that program? How was that program written? Isn't that a chicken and egg problem? Because if you wrote the source code of an assembler in assembly language using mnemonics and labels and stuff like that, then who is responsible to turn it into the executable? That's circular reasoning, okay? So that means somebody, some poor soul, actually had to write programs in zeros and ones with instead of assembly code to begin with. Does that make any sense to you? Okay. So do you want to look at a machine that's just like that, where you have to input programs, using zeros and ones and stuff like that? Okay, let's see that. And I cannot remember the name of that computer. It's one of the first computers. Okay, first personal computer. No, that's way too advanced. If you see a floppy disk drive and a keyboard, that's way too advanced. Okay, let me see. That usually they have it. I cannot remember the name.
Is it ENIAC?
Not ENIAC?
Not
Not ENIAC. It's a small computer, but maybe it's not personal computer. I cannot remember it. It is not ENIAC.
First portable.
I just cannot remember it. Okay, Intel. I know the processor it had was an 8080 processor computer. Okay, let's see if I can. Nope. Nope. Looks kind of like it. Okay, more images. That's it. AltAir, that's it. The name is the AltAir. All right, so this is an AltAir computer. And let me see if I can zoom into this picture, view picture by itself. Nope, that's not a zoom in. But now that I know the name, it makes it easy to search for that. So it's the AltAir computer. And because I want to focus on just the front panel, which is this part here. And it's kind of fuzzy. I suppose it's okay. It will suffice. Okay. That's your computer. That's your user interface. And you can tell this is actually pretty new because it has LEDs instead of light bulbs. So how do you input your program?
All the switches.
You see all the switches? Let me see if I can find out whether up is a 1 or not. It doesn't quite say, but I would assume, if you flip a toggle switch up, it is a 1. If you flip it down, it's a 0. So you basically flip a whole bunch of switches to specify the content. What about the address to store that content? A whole bunch of switches too. Okay, after you specify all of that stuff, do you remember your microcode machine? How do we store something into a register? We have a rising edge, right? So one of these switches here, I cannot really read the text, but one of these switches here is the clock. So you toggle that switch like tick tick like that, and it will store that one byte of content into a location in RAM. You have just successfully programmed one location of your entire program. What do you do next? Move on to the next byte. Flip all the switches, clock it, flip all the switches, clock it, and so on. If you make a mistake, you will find out when you try to run the program. Yes?
So how was it useful?
How was it useful?
Yeah.
Well, there was nothing like this before. So I think your question is what do people use it for, right?
Mm-hmm.
So that's actually your question. So for that, we can look up Wikipedia and find out what it can do, right? Okay. The AltAir also appealed to individuals and businesses that just wanted the computer to purchase the assembled version. It's widely recognized as the spark that ignited the microcomputer revolution. So that means if an alien species wants to halt the advance of humanity or human technology, they will go back and kill this machine because it kind of started the whole thing, including my modem. Okay, this is kind of like the starting point of this whole thing. The launch, descriptions, software. It even has BASIC, okay, which is an interpreter. Okay, so someone, in fact, the letter has been sent by Bill Gates and Paul Allen from the Boston area, and they had no BASIC yet to offer. When they called Roberts, who's the guy who came up with the AltAir design, to follow up on the letter he expressed in his interest, the two started to work on their BASIC interpreter using self-made simulator for the 8080 on the PDP-10 mini computer. Now this statement here, this is all very, very fascinating. Okay, if you think about this particular sentence, it's all fascinating because as it turns out, this machine is not really quote-unquote the first computer. There's no chicken and egg problem here. Why not? Because there were existing computers already, which is the PDP-10 mini computer. They wrote a simulator that ran on the PDP-10 computer, and they probably wrote the first assembler using a high-level programming language that ran on the PDP-10 computer. So they had bootstrap technology to make this work. So it's not really the first stage. If you look at this as a rocket, this is probably already like a third stage, rocket engine. It's not the first stage. This is way past the first stage. In other words, okay, let me rephrase this. This is similar to what we are doing in this class. We already have what? Logic sim. So we already have the tools to deal with a computer architecture. We can do everything in simulation. Okay. If I were to, once the toy architecture that we are trying to do is done, and I want you guys to actually write assembly code for that thing, you can actually write the assembler in C or C++, run it on your regular PC, but it cranks out opcode that the toy architecture can run. Is that making any sense? So in a way, you don't really have to do any programming without an assembler because you have cross-development platform, which basically means the architecture that runs the tool is different from the architecture that runs the object code of that tool. Does everybody understand what is cross-compiling? No? Yes? No? Okay. So cross-compiling is basically, okay, I'll give you a quick example. Let's say I want to develop a program for this watch. Okay. The watch runs an ARM7 processor, Snapdragon, which is a ARM architecture. But I can find a GCC tool that runs on a regular PC. So i7 is the processor of my computer. It runs a special version of GCC which cross-compiles to the ARM7 opcode. So the program will still be written in just regular C or C++, just like any other program that you have written. You go through the compiler. The name of the compiler is going to be a little bit different. It's going to be GCC-ARM7 or something like that. Okay. So the object code coming out of that compiler is not intended to run with an Intel processor. It is intended to run on a watch with an ARM7 processor. That's cross-compiling. In other words, the tool runs on a particular architecture, but the product of the tool running runs on another architecture. That's called cross-compiling. And that's what's happening here. Bill Gates and Paul Allen actually were doing cross-development because the development platform where they actually had all the tools installed is called a PDB-10 mini computer. But the code that runs, which is the basic interpreter, is going to the AltAir computer. I actually had the opportunity to do something like this at the end of my undergraduate study. So we were actually making the tools to create the code that would actually run on a different platform. It was a lot of fun. All right, so are we still doing okay so far with the concepts? We're still doing good? All right. So with this out of the way, I'm going to write a simple program, and I'll use GDB to illustrate all of the same concepts again, but it's just in a different way. Okay. So we'll go to a command prompt, anyone would do, and we'll just start to write a simple program. Nothing really important. Okay. So we'll say hello, and we all know this program. We all know this program except for the purist who decided cout is the only way to do things. All right, so here's the program. We do a GCC-G. Okay, I want to turn on debugging. Hello world, hello.c, GCC-O, hello, hello, hello. Okay, so we run the program in GDB. Hello, GDB, hello, like that. List the program, and we see the program in its source code in C and C++. Okay, in C actually in this case. So nothing really too important here. Okay, it doesn't seem to connect to what we were talking about in this class, in this particular class. Okay, so we'll go ahead and do something that will start to expose the stuff that we have been talking about. Okay, so the first thing I'm going to do is to put a breakpoint. Okay, so we'll put a breakpoint B on line 4. Okay, so it will stop execution on line 4. Run the program. Now it has stopped. Okay. Now, where it has stopped, I know exactly because the breakpoint is at this location. In other words, all the instructions have its own location, and this turns out to be the location of the first instruction to do the printf. Are we doing okay so far with that concept? Is that okay? All right. So now we'll go ahead and look at the X command. The X command is going to be extremely helpful in this class because what it does is it will examine memory and print out the content of that location. It is not that it is really useful, it's what it can print that is really useful. Because when you look at X/FMT, the FMT, which is the format part, can display numbers, it can display ASCII code, it can also display instructions. Okay, so if I specify X/I, it will display instructions. Okay, so this is what we'll do. So we'll say X/, I'll just say give me 5 instructions starting at the location. Which location are we talking about? This location. All right. So at this point, I have specified an instruction or a command in GDB to say examine show 5 instructions at location 804840C in hexadecimal. That's what I'm telling GDB to do. Are we doing okay so far? What are those instructions corresponding to in terms of source code? Printf. Okay, printf hello world. Okay, that's what I'm trying to do. But now I'm not looking at the source code. I'm looking at the mnemonic. Okay, because when it disassembles, it is showing you the mnemonic. Press the enter key. Okay, a whole bunch of instructions. Okay, it doesn't seem to make a whole lot of sense to us right now. Don't worry, it is not supposed to, because we have not talked about these instructions. We have not talked about the mnemonic. But nonetheless, do you see like a whole bunch of zeros and ones? No. We see something that we actually can read to a certain extent. Okay, so if I have talked about these instructions, I can actually, if I talk about it now, most of you will actually get most of them. Not all, but most. Sub is subtract. Push, we'll talk about that later. Call is call. Okay, it's just calling a function. Okay. Add is add. Move is kind of the same thing as copy. Okay, so it copies the constant 0 to the register EAX. Okay. So with some basic explanation of the syntax, most of you can look at this and go like, well, I can kind of make out what the program is doing. I don't know why it's doing it, but we can kind of make out some of it. Okay. ESP, by the way, stands for Enhanced Mode Stack Pointer. Okay. EAX is Enhanced Accumulator Register. Okay. The X stands for extended, E stands for enhanced. That kind of shows you the heritage of that register, because it has to be enhanced upon extended to come to the current state. You guys are not getting it? No. It's kind of like super duper ultra sterilized something. So they start with something, and then they say, oh, this is a super version of that, and then they'll say this is the ultra super version of that, and this is the ultimate. I cannot remember what I just said. Yes. Okay. So that's the nomenclature we're dealing with here. Okay. It is the enhanced extended register A, which stands for accumulator originally. Okay. But this is the mnemonic. What I'm going to show next is going to be even more interesting, because I'm going to look at one single instruction here and say, this is the mnemonic, but I want to look at the actual binary code of this. Okay? I want to look at the zeros and ones. How do I do that? Well, so what you need to do is to figure out what is the length of this instruction. It starts from location C and it ends at location D. Location E, so it takes up 3 bytes. Okay? Because C, D, and E, there are 3 bytes in the instruction. There are three bytes in this instruction, so there are 24 bits to this instruction. So the next thing I do in GDB is to say, I don't want to look at the mnemonics. Give me the binary code. So the binary code of 3 locations. Each location is a byte, and I want to display everything in binary. So that's what the 3BT means. The B is the unit of things that we're looking at. Before we were looking at units of instructions. Now we are looking at units of bytes. And the T has to do with how do you want to format a value? Okay, I want to format the value as a binary number. That's what the T stands for. And we'll use the same location, which is this location here. Press the enter key. that is the subtract instruction in binary code. The processor is going to take in these 3 bytes into the instruction register, decode it, retrieve the correct drum of the music box, roll it, so that inside the Intel i7 processor, it will do all the clocking, enabling the input of the register bank or output of the register bank, select the operation with the ALU, take the output of the ALU back into the register, store that and stuff like that. But that's all coming from this particular bit pattern. So are we making the connection, everything from high-level programming, like the C++ programming thing, all the way down to the mnemonic, which is something that is easy for us to understand, but it still needs to be translated, and all the way down to the binary code that is being stored in memory, and this is what the processor has to deal with. When we put this into the instruction register, the processor decodes it, finds out what it needs to do, roll the music box, the right drum of the music box, in order to execute all of those things by orchestrating all the subcomponents inside the processor architecture to get this done. So are we making a full connection between everything that we have talked about? Yeah. Okay? Not so much the detail. I don't need you to understand how do we write an assembler. Okay, that's not the point. The point is how do all of these things connect. Now if you want to extend that, all the way down to what we have talked about so far, then we can look and say, oh, inside the processor architecture, we have all of these components, some are called the multiplexers, we have adders, subtractors, and so on. But when you look into an adder, what do we get? Each adder has a whole bunch of full adders. Each full adder has 2 half adders. Each half adder has a bunch of gates, right? And then each gate, in return, can be translated into a configuration of transistors. So everything still boils down to transistors. But that's the entire path, okay? From a line of C code. Okay, I'm pretty sure some of you want me to not just say that, but to write it, right? So let's go ahead and write this, because I think this is going to be helpful. Okay, so we start with C code, right? And then we get into GDB, what do we see? Instead of C code, we can see the mnemonic. Mnemonic. And by the way, there's a movie with that word in it. What is it? Johnny Mnemonic, which is a fantastic movie. You should watch it. Not in class, okay? I know you guys want to do that. Okay, so mnemonic is really just a way so that we can understand the instructions easier. What is one level below that? The binary code. Okay, so binary opcode. So binary opcode. But the binary opcode, that's the lowest level of stuff that you can specify as a developer. Okay, you cannot go any lower level than that. Yep.
So it goes C++ or C.
Source code, any type of source code.
The source code, mnemonic, the binary.
Well, the mnemonic is kind of like an intermediate step, so that we can understand the instructions more easily.
Okay.
But to the processor doesn't see the mnemonics. The processor only sees the zeros and ones, the actual bit patterns.
Is it translated to assembly, or assembly is a...
Well, in this case, we are reversing the process. In this case, we start off with the binary code, and we come up with the mnemonics by means of a disassembler. Okay? And there's also a process called decompiling. Basically, you look at the object code of a program, and you try to come up with the actual source code of the binary code. It is a very difficult thing to do, and in the United States, it is actually illegal to decompile programs that you do not write. The DMCA probably covers a part of that, but there are specific rules that says decompiling is not legal. Yep.
Does it have anything to do with the reverse engineering?
Yes. Yep. So we have binary opcode. So binary opcode, I'll put a line here because this is the lowest level of stuff you can specify as a programmer. But below that, what do we have? We got microcode, right? Microcode, which are the things that we are doing with the previous homework assignment as well as the current homework assignment. We specify the microcode. So the microcode is nothing more than a whole long big chunk of sequence of zeros and ones to tell the individual parts of a process of what to do. So when we look down from microcode, what they're controlling, then we have the multiplexers, adders, subtractors, dividers, multipliers, and so on. Okay, all the bigger chunks of components. But each one of these can now be broken up into smaller components, like an adder can be broken up into, full adder. Full adder, becomes half adders, and then the half adder become, gates, and then the gates individually can become transistors. So that's kind of like a roadmap of all the concepts that we have talked about so far, and kind of in a sequence of, how did we go from transistors to C++ code. Is that okay so far? Because I don't want you guys to learn something that is completely compartmentalized to the point where I have no idea how this relates to everything else, but since it's going to be on the exam, I have to study. Okay, that's kind of the worst way to study for something, especially in computer science. Okay? All right, so now that we know this stuff, let's go ahead and write a very simple program, because I want to give you a sample program that does something, okay? So we'll go ahead and write the very first program in assembly. So I'll just call this add.s, and it doesn't do much. Okay, .text, .global. I'll explain all of this later, so don't worry if I don't explain what these things are. So we'll say move L $, okay, a particular number, okay, that turns out to be a pretty easy number, into a register. We'll copy another constant into another register. Move L into EBX, and then we'll do the add instruction. We're going to add EAX to EBX, but store the result into EBX. And then after this, we have some really kind of strange instruction here. I got it reversed, so I need to fix this. But I just want to show you, what an assembly language program looks like and how to write it. Okay, so this is just a text file. Okay, it's just a text file. I use VI to create this file. It has all the mnemonics, referring to the registers, labels, and whatnot. So the first that we have to do is to assemble the file, which is AS. That's the assembler. So AS-O to specify the output. Add.O is the object file. Add.S is the source code. So we are specifying both the output and the input file to the assembler. And since we want to debug it, we also have to specify G steps, not just -G, it's G steps. Okay, so this is done. We have to do the linking. The linking is done by LD, that's the name of the linker, -O to add, and the input to the linker is add.O. Okay, now we have the executable. So now we can do a GDB add, which is the executable. We do the L, because we included all the debug information. Now we can actually look at the source code as we debug this program. Just like with the C program, we can put a breakpoint. We can put a breakpoint on line 4, run the program, single step, and we can also look at individual registers. When you want to use print to look at individual registers, you have to precede each register name with a $, not a percent symbol. It's just a syntax thing. Okay, so it can display the content in decimal. You can print it out in hexadecimal. You can print it out in binary. So all of those formatting stuff that we talked about earlier also applies to print. Okay, we can single step. Okay, and then we can look at register EBX. Now EBX is updated, and then we single step one more time. We print the result of the whole operation in EBX. That seems like to be the right answer to adding 10,237 to 71,928, and that's it. Okay, this is kind of the whole development process. Okay, in a nutshell, this is what you guys will be doing for the rest of this semester. Now, obviously, you're not going to deal with programs of this kind of complexity, but the tool is the same. Okay, if you have learned how to use GDB in CISP 360 or some other classes, it's the same GDB. Okay, except in this case, we're going to be using GDB to debug assembly code. Okay, but a lot of the stuff that you learned already still applies. If you have never used GDB before, I wouldn't say it's hard to learn. Okay, you just have to replay the lecture, sometimes, and just jot down your notes to remember what command does what. Okay, and it's not really a difficult to use. It's just that you have to remember the commands. Are there any questions?
You put a GDB manual on Moodle, right?
Yes,
all
but
that.
that's a reference manual. You know, it basically is not a tutorial. It's
Okay.
intended as something like, oh, I remember the command is X, but I just cannot remember the details of how to use X. Then you look up the reference manual for that. As far as tutorial is concerned, the best way, you know, is just to, you know, watch the video again and just, you know, fast forward and pause, you know, where you need to, and then just write down your own notes. You know, that would be the best way to do it. All right, so we are running out of time right now. I will leave it up to you guys to do your homework assignment. Okay, so I will be in the lab if you know, need help with your homework assignment.